Hello and welcome to WCCI 2020. My name is Fayyaz Minhas and I would like to present our work on generalized neural framework for learning with rejection. In order to understand learning with rejection, consider the following scenario. Imagine an oncologist who has been given some data for a particular patient. If the oncologist is sure, based on, let's say, the test results that he or she has been given, they'll be able to generate a binary decision with high confidence. However, if they're not sure about their decision, then instead of saying yes or no to this question, that they'll simply say, I don't know, and will require some additional tests. This discovery of known unknowns or understanding what we don't know is a central feature of human rationality in decision making. We would like to reflect the same property in artificial intelligence in general and machine learning models in particular. That is, develop machine learning models that can generate a decision but also reject or abstain from generating a decision when they are not sure that their decision is going to be correct. The problem of learning with rejection can be formulated as follows. Just like traditional machine learning, we are given some training data. In a supervised setting, those would constitute training examples, their features, and associated labels or regression targets. The question is, what examples should we reject or abstain from generating a decision for at test time? However, unlike conventional machine learning or especially supervised machine learning models, we do not have any training examples for which we know that we should be rejecting these. So there are no training examples with a reject label. Our objective is to learn from given data to predict class labels as well as rejection labels, and that is what complicates this machine learning problem. A number of techniques can be used for learning with rejection. One simple way is to convert prediction outputs of a classifier to probability values using a softmax operation. Another approach can be to use ensemble methods and predict the confidence value for a given example based on difference between individual prediction scores of different models. Similarly, dropout can also be used as a means of modeling prediction confidence. However, the limitation of most of these methods is that they are restricted to classification and do not generalize either directly or well to other machine learning problems such as regression. You can read more about these existing methods and their limitations in the paper. In this work, we developed a generalized machine learning model for learning with rejection that can be applied to classification as well as regression and possibly other machine learning problems. The proposed solution is based on training two separate models, a prediction model h of x and a rejector model r of x, each with their own architecture and trainable parameters, which are obtained by minimizing a novel meta-loss function. The rejection model is responsible for generating a rejection score, which is based on the degree of confidence of the prediction model for a given example and can be used to reject examples at test time. This division of the prediction and rejection problems into two separate models is motivated by the fact that this allows us to model any type of machine learning problem with rejection, be it classification or regression. Another reason for this is that typically the rejection function will need to be more complex in comparison to the prediction function, and we will demonstrate that in our results as well. At inference, a prediction from the prediction model is only accepted if the corresponding rejection score R of x is greater than 0. There are three objectives of training a learning with rejection model. Number one, reduce errors over training data, just like any other machine learning model. Reject examples for which the predictor is expected to produce large errors, and keep the number of rejections small in order to avoid a trivial solution. In this work, we propose to achieve these three objectives by using a meta-loss function, capital L, which penalizes large training errors using a non-negative loss function for the predictor, while minimizing the number of examples that will be rejected using a rejection cost hyperparameter, C. As can be seen in the plot on the right, in which we plot the rejection model score on the x-axis and the prediction loss on the y-axis, the meta-loss function penalizes rejections when the prediction loss is small, as well as large negative rejection scores. To summarize, we propose using two separate machine learning models, each of which can be a neural network with a shared meta-loss function. The proposed solution is generalized in the sense that it allows to solve any machine learning problem with a reject option. The proposed meta loss function is convex with respect to the rejection output and the prediction loss, which aids in faster convergence. The proposed model also gives the flexibility of either training both the predictor and rejector models simultaneously or training the rejection model after the prediction model has already been trained. It also allows different features to be used for rejection and prediction in a heterogeneous feature space scenario. The plot on your screen shows the results of training simple neural networks on toy problems with the proposed approach. The decision boundary learned by the predictor is shown in black, whereas the rejection boundary is shown in green. As can be seen in this plot, both the rejection and prediction models have been able to learn their respective decision boundaries. The overlapping region between the two classes will be rejected. If we plot the AUC ROC versus the number of rejections for this model, it can be clearly seen that the learned rejector discards confusing examples, which results in improving the AUC ROC with increase in number of rejections, whereas random rejections do not yield any such improvement. The bottom plot shows a more complicated example of the proposed model in action with similar results. Another observation that can be seen over here, especially in the top row, is that the rejection boundary is much more complex in comparison to the prediction boundary. This justifies the use of two separate models or models with different capacities for the two different components in our proposed approach. We have also evaluated the performance of the proposed method for learning with rejection over both classification and regression problems from the UCI repository. For classification, the proposed model performs as well as DHL and CHR methods. However, unlike these methods, the proposed approach is directly applicable to regression problems where it yields improved prediction performance in terms of mean squared error in comparison to selective net, which is another approach capable of learning with rejection over regression data. We have also applied the proposed approach to our machine learning-based hurricane intensity predictor called Fury, which has been developed in collaboration with the National Hurricane Center in the US. Fury is a regression model that uses satellite infrared imagery of hurricanes to predict their intensity based on a set of statistical features. However, satellite imagery can contain noise and other aberrations which need to be rejected. For these experiments, Fury predicts the intensities of hurricane images from various hurricane seasons after being trained on data from other seasons. We have used the proposed LWR method for training a predictor and a rejector model in order to reject examples for which the model predictions are expected to be confusing or with low confidence. As can be seen in the table above, the proposed LWR approach is able to improve the prediction root mean square error in knots for this regression problem. Specifically, without rejections, we get an RMSE of 13.8, which reduces to 12.3 when the rejection fraction is about 10%. In contrast, random rejections do not yield any performance improvement. These results clearly show that the proposed model is effective in a practical scenario. Here we look at different images that have been rejected. Notice the large errors of the predictor for these examples. This clearly shows that the rejection function has correctly identified these cases without having access to the ground truth intensities. In conclusion, we have developed a generalized method for learning with abstention for classification as well as regression problems. We have demonstrated that the proposed method is applicable to a wide variety of problems from UCI repository datasets as well as in a practical setting on satellite imagery data. We have also demonstrated the effectiveness or the behavior of the proposed method over toy examples. We think that the proposed approach can be very effectively used in a variety of other settings such as biomedical, cancer prediction, economic prediction models. It can also be applied in other meteorological models. It would also be interesting to explore other types of machine learning problems for which this approach can be used. The code for the proposed method is available on GitHub at the link provided. It has been nice presenting at this conference, and I would like to thank Pathlake for their sponsoring my participation in this conference. Thank you.